We have a couple of announcements before we get started. The first one is midterm exam. We'll try to finish it by the end of this week, and you should be able to see it. The next one is on discussion worksheet. So as you can see, we're tidying up some of the loose end here. So I wish to finish IR and mass back before midterm 2, and I didn't manage to do it. So this week, the worksheet will be graded based on your completeness because we are still working on IR and mass back. So that means you'll keep learning while your TAs are having discussion session with you. So today and on Friday, we'll finish our topic on spectroscopy. That is, today we'll talk about IR spectroscopy. On Friday, we'll go over mass spectrometry. You will see these problems on your discussion worksheet, but again, just try it out and your TA are only graded based on completeness. We'll have more IR and mass spec practice problems on your next week's assignment, either on Canvas or on discussion worksheet for you to practice on. All right. Next up, I posted a new Canvas assignment on Brewing Learn. You should be able to see it. The topic is on proton NMR, and that is due by the end of Friday, so you should still have plenty of time to work on it. I'll also post new Canvas assignment on IR and mass spec when we finish it up. And one last thing, Professor Neil Gard, who is also our department chair, shared with me a good opportunity. You should try it out. The department is trying to introduce virtual reality or VR for you to visualize the molecules. As you probably already know, like working on stereochemistry and also conformations, having a molecular kit, being able to see the molecule in three-dimensional is very helpful for you to understand the topic. So, I forgot my mic. So if you have the chance, click the link and sign up for that opportunity and see what's coming out of it. All right. Any questions on the administrative things? Yes. The one of the Canvas assignment on proton NMR. It's either this Friday or next Friday. I forgot what's it. Okay, next Friday then, that's my bad. But I gave you plenty of time so you can work on it, but that's the Canvas assignment on the proton NMR. All right, any other questions? Nope? All right, sounds good. So we're approaching to the end of the quarter. We have 6 more lectures together before we reach the buffer lecture or we're ready for our final exam. As you probably know, we're a little bit behind on our designated schedule on syllabus. So here I want to give you a brief overview in what to expect in the coming 6 lectures because I changed the structure a little bit. I also talked to your 14D instructor to make sure I'm covering absolutely necessary stuff you need to success in 14D. So here are a few topics. We'll continue working on spectroscopy, IR, and mass spec on today and Friday. Next Monday is Memorial Day. It's a national holiday, so we'll not meet next Monday. Next Wednesday, or May 31st, we'll have a lecture on using the mixed spectroscopy method to solve for molecular structures. So in that lecture, we'll also tie up some of the loose end, like carbon NMR, and also degree of unsaturation, and also how to use IR, mass spec, NMR, degree of unsaturation, molecular structure, and everything to solve for the molecular structure of an unknown molecule. Like you know nothing about it. Now you have all these spectrums. How do we derive the molecular structure of a molecule? So that's our May 31st. After that, we'll spend 1 lecture talking about conformation of cycloalkenes. So we've seen lots of rings before. We were talking about cyclobutane, cyclopentane, and how to get an idea about what are the mirror plane in between and what are the cis and trans relationship between all the substitutions on those cycloalkane. But so far, I've been avoiding talking about cyclohexane or the 6-member ring. So 6-member ring is special. It is a relatively strain-free molecule, and we have chair and boat and like half-chair conformations we need to talk about. So on June 2nd, we'll talk about conformation of cycloalkanes. And in there, I highlighted the chapter 4-3, which is the chair conformation section. We'll be focusing on the cyclohexane. All right. And on our last two lectures, we'll be talking about non-covalent interactions and biomolecules. It looks like a very large, extended topic. So what we're trying to do here is trying to introduce to you, now we know what are chemical bonds, right? In like CH4, we know we have 4 carbon-hydrogen single bond. But in reality, when we're talking about biomolecules, like those bigger proteins, or DNA, or your fatty acid, on top of the covalent interaction or chemical bond formation, we have multiple non-covalent interactions that help to hold those big structures together. So in our last two lectures, I'll basically fuse the non-covalent interaction like hydrogen bonding or dispersion interaction or the pi-pi interaction. We'll fuse those topics in when we're introducing very basic biomolecules, like what are amino acids, how do amino acids make peptides, and how do peptides fold into your protein structure. Or when we're talking about fatty acid, what are fatty acids, what are carbohydrates. So these two will be quick introduction to biomolecules, and also we'll focus on the chemistry there, or we'll focus on how does non-covalent interactions contribute to your structures of those biomolecules in our body. And ideally, that should call to the end of our entire quarter. So it's a little bit update to what's already on the syllabus, but we're still covering whatever you need to be successful in 14D. All right, any questions on that topic? Yes. You can find that on your MyUCLA the registration office decided. Your final exam is going to be in person, and again, we'll grade your exam. We haven't decided whether we want to do it on paper or on Grayscope. We'll have more information when the time comes. Okay, any other questions? Nope? Okay, sounds good. So let's get back to our IR spectroscopy. So IR spectroscopy or infrared spectroscopy. I think in this section, I briefly went over the Bohr-Oppenheimer approximation and also the spectroscopy method. But it's been a while, and let's just restart everything for the entire lecture and pretend like this is the first time you see these slides. So today on IR spectroscopy, we'll have, 3 pieces of information. The first piece is theoretical background. What are the information we get by reading the IR spectroscopy, and how do we read the IR spectroscopy to get information about functional group in your IR spectroscopy? And then we'll work on 2 sample studies. That means like what kind of question you should expect, or what kind of information you can get. Or like now we know the IR spectrum looks like, how do we derive molecular structure from the IR spectroscopy? Okay, getting started. The first thing first, that's a quick review. Whenever we're talking about spectroscopy, especially we're talking about the movement of the nuclei, not the electrons. So far when we talk about the UV-Vis spectroscopy, we're talking about the energy difference between different electronic energy levels, right? So when you're taking a measurement of the UV-Vis spectroscopy, what is happening is the electron is jumping from a lower lying molecular orbital to a higher lying molecular orbital. And using the UV-Vis spectroscopy, we're measuring the difference between your different molecular orbitals. You're getting information about electronic states by taking measurement using the UV-Vis spectroscopy. And then we move on to talk about NMR, where we're talking about the nuclear spin state that's flipping in your NMR state. We're talking about energy difference between either it's your spin state is going along with the external magnetic field, or it's going against the external magnetic field. So that being said, we're chemists. We care about the movement not only of the electrons, but also for the nuclei. But at the same time, in order for us to get any information out of it, we want to have the hypothesis that's supporting us to look at our nuclei movement without worrying about how the electrons are going to move according to your nuclei movement. So that's why I want to quickly introduce the Bohr-Oppenheimer approximation, or the take-home message here is using the Bohr-Oppenheimer approximation, what we can say is that the motions of your nuclei in your molecule, they are independent to the motions of the electrons in your molecule. So when we're talking about a bond, it's like stretching, so your nuclei is moving, we're not worrying about how the electrons are moving along with the nuclei. Rather, what we're talking about is electrons are acting as a delocalized electron cloud that's not changing too much when the nuclei are moving around. So again, this is one of the fundamental hypotheses in spectroscopy that people make. The idea here is simple. The idea here is by observing the nuclei and the electrons, what we say is the nuclei movement is much slower comparing to the movement of the electron, or the speed of the movement of your nuclei is much smaller comparing to the speed of the movement of your electron. So in the point of view of your nuclei, if we're solving for the electronic wave function, the electrons are seeing your nuclei as just a fixed item. So it's like if you are in a train or in an airplane and you look at someone walking on the street, that person appears to be like not moving from your perspective. And on the other hand, when the nuclei sees the electrons, because the electrons is moving so fast around those nuclei, electrons just feel the nuclei as a delocalized potential. So the nuclei doesn't care what's the exact position of the electrons. So nevertheless, this is a very quick introduction in the fundamental hypothesis of all spectroscopy, which is the Born-Oppenheimer approximation. And then moving on to our theoretical background for IR spectroscopy. So, in any spectroscopy method, when we're talking about the absorption of light, what we're saying is now your molecule, whether it's the nuclei or the electron, so your molecule is gaining energy from an external source. And that energy is in form of a photon. Right, so in spectroscopy, we're shining light or electromagnetic radiation onto a sample. That sample is going to absorb that energy and react to that energy, depending on what kind of energy level we have. So in your molecule, you have multiple quantum states that are quantized. You have electronic states. You also have vibrational state, rotational state, translational state, and also spin state. So all these energy states are quantized. And according to quantum mechanics, whenever the wavelength or the delta E of the incoming photon matches the difference between your initial state and the final state, we can observe something out of it. We can get some information about the molecule. So in any spectroscopy, what we're talking about is your sample absorbing some kind of energy. Your sample absorbing a photon, and that photon carries a little packet of energy. And if that packet of energy happen to align with some of the delta E within different energy state in your molecule, we can get information out in spectroscopy. So that's a fundamental idea of spectroscopy. And then in our chemical molecule, we have different kind of energy we can talk about. We have electronic energy, vibrational energy, rotational energy, and translational energy, and also nuclear spin. And these energy tells you different information about your molecule. All right, so this is a quick introduction in, again, spectroscopy. So there are multiple spectroscopy methods. Like what we were saying, depending on what kind of wavelengths you're using, you're exciting different kind of motions, whether it's electron movement or you're vibrating the nuclei or rotation of the nuclei. Depending on what the wavelengths we're using, you can get different kind of information about your molecule. Or the other way to put it is we use light of different wavelengths and accordingly different spectral region or different energy to find different molecular information. So here's a quick summary table on what people use to find what kind of information. Some of them are not covered in this class. Some of them have already been discussed. And today we'll work on the IR spectrum. So if we look at it, here we start from the lowest energy or the largest wavelength of light we're using in our spectroscopy. And the one with the lowest energy or the largest wavelength is our radio wave. And if you remember in NMR or nuclear magnetic resonance, we use radio wave to get information about the energy difference between two different nuclei spin states. All right, and we have spent numerous time in talking about NMR and how useful NMR are by telling us information about the bonding environment and consequently molecular structures of your molecule. And keep going. The next spectroscopy method we have are the rotational spectroscopy. This one we're not going to cover, but rotational spectroscopy will tell you information of bond length, bond angle, and etc. Today we'll be focusing on talking about the infrared or near-infrared spectroscopy. So it's called near-infrared because this wavelength is in the near-infrared region if you look at an electromagnetic spectrum. It's a vibrational spectroscopy. It tells you information about bond force constant or how polar and how strong your bond is. Also tells you information about the reduced mass or what's the atomic mass of the atom of that specific vibrational mode. If we keep going on the table, we'll reach this point of the UV-vis spectroscopy that we were talking about. Again, UV-vis spectroscopy gives you information about the electronic energy state. So let's say in your HOMO, you have 2 electrons, and in your LUMO, it is empty, right? So upon absorption of light, we end up having an excited state with 1 in the HOMO and 1 in the LUMO. And this process, we're exciting the electron to go from your HOMO to the LUMO. And at the end, when we keep increasing the energy or keep decreasing the wavelength of your light you're using, we can excite our core electron. So UV-vis, we're only talking about valence electrons or the outer shell electrons that are easier to be excited. But using X-ray, you can potentially excite the core electrons so you can get information like ionization energy and etc. Like for example, if we're talking about oxygen, the valence we're talking about is likely to be 2s and 2p atomic orbitals. But using X-ray, you can potentially excite the 1s electron of your oxygen as well. Nevertheless, so this is a quick summary on the spectroscopy method people can use in chemistry. We went over 3 of them, and there are some that's being left for you to explore in the future. All right, so let's move on to talk about our vibrational spectroscopy. So one of the things of vibrational spectroscopy, one of the fundamental questions we want to ask ourselves is what exactly we're talking about. How come your chemical bond is vibrating? If you have molecular kit, be like, oh, that's just a rigid stick. But in reality, when we're talking about molecules, let's just use a diatomic molecule. Imagine a molecule like, HF or maybe HCl. We're just talking about one molecule with 2 atoms only. And these molecules or these chemical bonds can actually expand and contract like 2 balls on a spring. So those chemical bonds are not rigid. They're not just a rigid stick. And their behavior can be roughly described using Hooke's law. So Hooke's law is one of the fundamental laws physicists use to describe performance of the spring and gives you a harmonic oscillator. So approximately, chemists also use Hooke's law to describe the vibrational motion in a molecule. We'll spend some time looking at Hooke's law. So here's the general form of Hooke's law. So here we have several different parts. The first part here, that's the wave number. We briefly touched on it. So that's a vibrational frequency in a different unit called wave number. And then in this formula, we have K as a constant, F as our frequency. That this frequency is different from the left frequency. I'm sorry, that's not frequency. That's a force constant. So F is our force constant, or how stiff your chemical bond is, and mu is our reduced mass. So we'll go over them one by one. Let's look at the first one. The first one here is our wave number. And wave number is calculated by taking 1 over the wavelength of your molecule. And the wave number will have a unit in centimeter -1. All right, so your wave number will have a Cm minus 1, and that Cm minus 1 comes from 1 divided by your wavelength of the light you're using. And in this case, you can do that calculation, find out that 1 wave number is equivalent to, say, the frequency is equal to 30 times 10 to the 9 hertz. So this one is just a quick introduction in what's a typical unit people use in spectroscopy. Let me just copy paste this down so we're talking about it while looking at the equation. Now let's focusing on this force constant. This K is just a constant we don't care about, and F is the force constant that's chemically relevant. So the force constant F tells us information about the stiffness of the bond, or how easy or how hard it is to compress that little spring, if we're talking about it. So naturally, we have some trend you might want to know when we're talking about the stiffness of the chemical bond. Imagine now you have a more stiff bond, or you have a spring that is hard to be contract, or and also hard to be elongate. So in that process, what we are talking about is stronger and more polar bond will tend to have larger stiffness or larger force constant F. And in this relationship here, what we have is this wave number, or your frequency, equals to K constant times square root of force constant over mu. Let's ignore mu for now. But what we're saying is if our force constant is larger, we're expecting our wave number to be larger. All right, so taking these two pieces of information together, you can rationalize some of the trend in what kind of chemical bond you expect to have larger wave number. So some of the trend we have here will be, let's compare maybe a triple bond with a double bond with a single bond. So we know that triple bond is stronger than a double bond than a single bond. So naturally, what we're expecting is let's say carbon-carbon triple bond will have a larger wave number comparing to a double-double bond and comparing to a single bond. So here, this kind of trend, I do not expect you to give me any quantitative answer. Rather, it's like when looking at the spectrum, when you look at that big IR spectroscopy table, you can get some chemical information out of it, like without knowing the exact number of these vibrational frequencies. So that's the chemical bond that's stronger. And what about polarity? So recall polarity. For example, if we have a chemical bond like HF versus HCl, what we have is your hydrogen has a partial positive charge, your fluorine has a partial negative charge because of electronegativity. So naturally, we can draw the dipole moment of that bond along the direction of your partial charges. And in our HCl case, what we have is you still have the partial positive and partial negative, but now we know your chlorine is less electronegative compared to fluorine. As a result, the polarity of your HCl bond will be smaller comparing to the polarity of your HF bonds. And also the trend goes on, right? OH is more polar than NH, than CH, etc. So if we're looking at the trend, what we have, if we're talking about the polarity, we'll have like HF will be larger than HCl. And also at the same time, if we're talking about OH, will be larger than NH than CH. So these are coming from polarity. All right, so three pieces of information. The first piece of information, we're making the connection between larger force constant as equivalent to say, or proportional to say we're expecting to have larger frequency or larger wave number. So that information we get by look at Hooke's law. Then we have two pieces of information you can derive. The first piece is we know that stronger bond gives you larger force constant. So stronger bond tend to give you larger wave number in IR spectroscopy. And then more polar bond will have larger force constant, and more polar bond will likely to give you larger wave number in your IR spectroscopy. All right, and now we have our reduced mass. So I'm just gonna copy paste this down again. So now we're talking about our reduced mass, or our mu here. Reduced mass is defined by M1, M2 divided by M1 plus M2. And here, M, just say that's a mass of your atom that's binded onto your, in your molecule or in that specific chemical bond. Let's look at some examples together. Let's say we have OH. Again, we have the reduced mass defined to be M1, M2 divided by M1 plus M2. So if we're looking at the oxygen-oxygen bond, whether it's a double bond, single bond, it doesn't matter. It's just a chemical bond between your oxygen and oxygen atom. The reduced mass of that oxygen-oxygen bond will be 16 times 16 divided by 16 plus 16. All right, so that mass, these mass are the mass of your oxygen atom. And doing that calculation, you get about 8. If we're talking about carbon-oxygen bonds, we have 16 times 12 divided by 16 plus 12. So that will give you a number of 6.86. So it's carefully reflecting the overall mass of your two atom system. For a carbon-carbon system, we're expecting our reduced mass to be smaller. So likewise, you have 12 times 12 divided by 12 plus 12. You end up having 6, which is way still smaller comparing to CO and then comparing to OO. And then when we're talking about a molecule with hydrogen, now the trend becomes very obvious. We have 16 times 1 on the top and 16 plus 1 on the bottom. We end up having 0.94. So overall, what we have is if you have lighter atom bonded in that specific chemical bond, or we're talking about a chemical bond with a lighter atom, we're expecting it to have a larger or smaller, we're expecting lighter atom to give you smaller reduced mass and consequently larger wave number. So the idea here is, let's say, that's the Hooke's law we're talking about. We have mu on the bottom of your equation, or the reduced mass on the bottom of your equation. So your lighter atom with lower atomic mass will give you smaller mu and consequently give you larger wave number or larger frequency. So for example, if we're talking about the stretching or the vibrational mode, the frequency of a OH vibrational mode comparing to a OO vibrational mode, you're expecting the OH to have larger frequency. All right? So the take-home message here, by just looking at the Hooke's law, we can get a few information. The first piece of information, again, this is a Hooke's law we've been talking about. And as a reminder, this mu here, just say that's the wave number. That equals to 1 over lambda, or lambda is your wavelength. And then K here is a constant that's not chemically relevant. And this F here is our force constant. in general, when we have an increased number of force constant that's coming from stronger and more polar bonds, we're expecting it to have larger frequency. And this mu here, what we're talking about is when we're having smaller mu, we're expecting it to have larger frequency. All right, so lighter atom will give you larger vibrational frequencies. And before I pause to, well, actually let me just pause here and see if we have any questions on Hooke's law. All right? Okay, sounds good. And then let's just, before we move on to look at specific chemical examples, I want to just quickly emphasize that for each electronic state, you will have multiple vibrational states. So in this case, I'm just taking this blue curve here as our ground electronic state. All right, so this entire curve is your electronic state. And in this curve, you can have multiple vibrational states. And each of these vibrational states, the difference between these vibrational states are combinations of different normal mode. So when your molecule absorbs a photon, it is jumping from different vibrational states within the same electronic state. Our IR or infrared does not have enough energy for your electron to move. So if you imagine, we'll have a higher electronic state, maybe somewhere here. Let's just assuming that's your excited electronic state. So when we're talking about IR spectroscopy, we're talking about the vibrational quantum levels within the same electronic state. And again, when we're talking about vibrational energy levels, we're only talking about excitation of vibrational mode. We're using our infrared as our light source. The wavelength is in between like 3 times negative 4 to 3 times negative 6. And now let's see some examples and see how things can get complicated. Right now it looks like, oh, it's just Hooke's law, how bad can it be? But in reality, when we're talking about, I know. So when we're talking about polyatomic molecules, we'll use water as an example. Water only has 3 atoms. Now instead of 2 atoms, instead of one single stretching, the combination of different kind of stretching mode makes these IR spectroscopy complicated. So when we're looking at polyatomic molecules, the vibrational modes are represented by superposition of different normal modes. So what does normal mode mean? I'm going to quickly show you an example here. So these are the normal mode of water. So in the IR spectroscopy, in the IR table, you'll potentially see, you'll see lots of different names, right? You'll have like CO stretching or CH2 bending. What does those terms mean? So those terms actually mean a specific normal mode, a specific vibrational mode in your molecule. So water is already pretty straightforward. You only have 3 normal modes. And in reality, how this water molecule is moving, it's a superposition of all 3 modes moving together. So in the IR spectroscopy, we're not going to do any analysis that's quantitative. Rather, we'll do it in a qualitative fashion. So here are some of the normal modes of water in the bent geometry. So I actually calculated them using quantum mechanics calculation. It's pretty fun to look at. So you have at least one symmetric stretch. That means your oxygen and hydrogen bond are just symmetrically stretching with each other. Their forces are to the same direction. We have symmetric stretching. You can imagine we also have anti-symmetric stretching. So that means your hydrogen are moving in different direction in your water molecule. So those 2 are the stretching mode of your water molecule, or the OH stretching. And plus, that's one of the reasons you cannot use IR to distinguish these 2 oxygen-hydrogen bonds, because you have symmetric stretching, you have anti-symmetric stretching, and what we're observing is actually a superposition of both stretching together. All right, next up we have the bending. So this one tends to have weaker intensity because the dipole moment change is small along the process of your nuclei movement. So bending is basically say your oxygen is like going up and down, and your hydrogen is going up and down along with it. I'm not going to test you on these figures. I just think it's really cool to show you how your molecules are actually moving, how your chemical bonds are actually like compressing and stretching while we are talking about it like a stick. Okay, any questions before we move on? Nope? Sounds good? All right. IR spectroscopy. So now we know the complicated nature. Now we know the theoretical background of IR spectroscopy. The question comes, as we as organic chemists, how do we get information out by looking at an IR spectrum? Like how to read the IR spectrum? We did the same thing with our proton NMR. Let's do the same for our IR spectrum as well. So this is a, well, IR spectrum of our so far favorite molecule, ethanol, or your alcohol. In this spectrum, in any scientific spectrum, the first thing first is you look at the x-axis and the y-axis, right? Remember on your proton NMR, the x-axis is chemical shift. The y-axis, well, that's less important. But in the IR spectrum, both axes are important. On the x-axis, we have our wave number. And remember, we have our Hooke's law to describe our wave number. That equals to constant times the square root of force constant divided by your reduced mass. All right, so the position of the peak depends on the x-axis. And the position of the peak gives you information about reduced mass, about the force constant of that chemical bond. On the y-axis, this one is a little bit special because if you read it, that's called the transmittance. So what it means is this one is reversed. So at the top, when we're having 100%, what we're saying is light just directly pass through your molecule without being absorbed. So whenever your peak is at higher, that means we have no absorbance. Or the other way to put it is like the peaks in the IR spectrum are pointing down. All right. So now how do we read this? How do we read this kind of spectrum? Again, we have the same kind of information we had before. Remember looking at this one? Well, we'll have stronger bond. We're expecting it to have larger wave number and also bonds with lighter atoms will have larger frequency. And then at the same time, when we're having more polar bonds, we're expecting to have more intense absorptions. So these are known information we just derived. And let's look at two peaks in this figure. And I'm just gonna telling you one of them. In these two peaks, oh, let me use a different color. We have this one, and then we have this one. So one of them is a OH stretch, and one of them is a CH stretch. Right, we're talking about alcohol. In your ethanol molecule, you have CH and OH bond. One of these peaks are OH stretch, one of these peaks are CH stretch. Which one is which? So remember, the more polar bond will have larger absorption, and OH is a stronger bond comparing to your CH bond. So my green one is my OH, and that smaller one will be my CH stretch. And just to quickly comment on the broadness of our OH stretching, we keep talking about hydrogen bonding between your OH group, NH group, or SH group with the solvent. So again, in your IR spectroscopy, the same kind of observation is happening. So your OH is continuously making hydrogen bond with a solvent, and as a result, it is showing that broad peak. All right? So let's look at some more information you can get. So here's a full table, which is also appeared on your table 11.4. What we expect you to know is use this table to get information about functional group. So different kind of functional group will give you different kind of stretching pattern or spectrum pattern, if you may. Like what we were just talking about, the OH bond in your alcohol carboxylic acid, they will tend to give very broad and strong absorption peak. So like the peak we were showing before, this is the typical range. You will see OH between 3200 wave number to 3650 wave number. And if we go back to this figure here, and remember that's the range we're expecting it to be, and that's exactly where we see that broad peak, which is iconic for OH stretching. So the take-home message here is read the table and get information from the table by looking at the spectrum. Or the other way to put it is if I give you this table without telling you anything about the molecule, just because there is a peak, there's a broad peak in between that 3200 to 3650 region, you can tell, oh, we have a OH group in my molecule. All right, so that's how to use that table. We have lots of table there, and again, one of the things I want you to keep in mind is try to connect these numbers. Like, don't remember this table, like just please don't. It's open book, and there's no point of it. Just look at the table and know how to use it. Like in this case, we're talking about the OH group in your alcohol and your carboxylic acid. Your carboxylic acid has OH has a smaller wave number, and why that's the case? It's because this bond is a weaker OH bond comparing to the OH bond in your alcohol group, etc. Or if we're comparing the ROH with the NH there, and we see the NH are expecting it to give you a smaller wave number comparing to your OH group. And again, that is because your NH is slightly less polar. Nevertheless, I'm not gonna go over all of these terms. You might see some of the rationalization question on your Canvas assignment. I'll be like giving you two pairs and ask you to say, all right, now you look at alkyne and alkene, can you tell me why alkyne have a larger wave number peak we expect, all right? So those are the kind of question you will see on your assignment. And the other possible way we ask the question is now I give you the IR absorption, or what it means is I give you the IR absorption here. We have the alkyne CH, we have the alkene CH, and the alkane CH. And in this case, we have the alkyne CH to have the larger wave number absorption. The alkene CH has the medium, and the alkane CH has the smallest wave number absorption. And I can ask you to rank the CH bond strength in the following molecule. So by reading the table, we know that the alkyne CH has a stronger bond, the alkane is the medium, and the alkane, or the sp3CH, have the smallest wave number. So as a result, we know this is a stronger bond, this is a medium strength, that's the weakest CH bond along the range. All right. And one of the most important way people use IR spectroscopy is to identify those key functional groups. And I really want to highlight one of the iconic stretching you should definitely be looking at in your IR spectrum. Whether or not you have that stretching tells you lots of information. So that is our carbonyl group. So a carbonyl group is often observed in your functional groups, including like aldehyde, ketones, esters, carboxylic acid. It is a carbon-oxygen double bond. So if you think about a carbon-oxygen double bond, so first of all, this one is a very polar bond. So the good thing about the carbonyl group, the carbon-oxygen double bond being a very polar bond, it's telling you we're having a strong IR signal, IR absorption. So when we say we have a strong IR absorption, what we're saying is that peak that's going down is going to be really big. And that's easy to identify. And by searching for the, present or absent of that peak in your IR spectrum, you can quickly tell whether or not my molecule has a carbon-oxygen double bond. So two important things to look at. One, the carbon-oxygen double bond that is in the region of about, 1700. It's going to be a strong, sharp absorption peak. The second piece of information that's very iconic are your OH, NH, so those like group that can make hydrogen bonding with your solvent that gives you very broad peak. So let's look at some example. So this is a typical example I would ask you to work on. So let's look at the molecular structure. We have an oxygen in your C5H10O. Well, the first thing, of course, you can do is look at your molecule and make sure the number of atoms are matched up. So we can take over this molecule here, because if you count the number of hydrogens, it have more than 10 hydrogens. And the next up, we can look at these molecules. And looking at this IR spectrum, what we have is this big, iconic alcohol. Right, it is a super broad peak that is like stretching. So this tells me my molecule will have an alcohol or an OH group in it. And the only molecule has OH group is this one. All right, so IR spectroscopy is really good in identifying some key functional group once you're familiar with it. Alcohol is one of the easy ones. And let's look at a second example. Now here we have the C6H12NO. Well, unfortunately, this time we cannot rule out, we can rule out one of it. This one has 2 oxygens, so obviously it's not our first one. And comparing these two, now the middle one has a carbonyl group or a carbon-oxygen double bond, and the right one is an alcohol group with an OH bond. So 2 pieces of information. The first thing is we no longer have that alcohol, OH, broad peak anymore. And at the same time, we have this peak. Remember, it's about 1700 wave number, and it is a sharp, strong absorption. And that's corresponding to our carbonyl group. All right, and in this middle molecule, we have the carbonyl group that's corresponding to that big peak there. The IR spectroscopy are more complicated than what I just showed you, but the take-home message here is, again, if you're gonna remember anything in reading your IR spectrum, first look for that oxygen OH stretching in that high wave number range to identify any OH group. And second, search for that carbonyl group in your 1700 region to see if you have a carbon-oxygen double bond. And for other information, you can refer to the table and see if you can assign the peaks. And also, one last thing, you're not going to be able to assign for every peak in your IR spectroscopy. All right, just looking at those iconic peaks, you do not need to assign for every peak in your IR spectrum, not like a proton NMR. All right, that's it. I'll see you on Friday. 1 second.
Oh, no problem. Yes. I have a question about the last slide that you just did.